Welcome to this lecture on evaluation metrics, weight of evidence, and information value. In this session, we will cover everything you need to assess and improve a classification model, from the confusion matrix all the way to advanced feature selection using WOE and IV. This is a core topic for any machine learning interview, so pay close attention. Let us begin. Let us quickly recap logistic regression before we move to evaluation. The logistic regression model outputs a probability between 0 and 1 using the sigmoid function. The cost function is called log loss, and it is minimized using gradient descent. Now, the key point: once we have a probability, we need to make a class decision. By default, we use a cutoff of 0.5. If the probability is greater than or equal to 0.5, we predict class 1. If it is less than 0.5, we predict class 0. But here is the important insight: the cutoff is not always 0.5. If class 1 needs priority, for example, detecting fraud or disease, we should lower the cutoff to catch more positive cases. The business team will always help you decide the optimal cutoff for production. Now, let us understand the confusion matrix. When a model makes predictions, 4 outcomes are possible. True positive, actual is 1. Predicted is 1. Correct. True negative, actual is 0. Predicted is 0. Also correct. False positive, actual is 0, but we predicted 1. This is a type 1 error. False negative, actual is 1. But we predicted 0. This is a type 2 error. In our example with 180 samples, 100 true positives, 50 true negatives, 10 false positives, and 20 false negatives. Accuracy equals TP plus TN divided by the total, which gives us 83%. 1 minus accuracy is the misclassification rate. But accuracy alone can be misleading. On an imbalanced dataset, a model that always predicts 0 can get 95% accuracy, while being completely useless. This is why we need other metrics. Let us look at 3 real-world use cases to understand when FP and FN matter. Use case 1, diabetes detection. Here, a false negative, missing a diabetic patient, is dangerous. The patient goes untreated, so we want high recall in this case. Use case 2, legal, convicted versus innocent. Here, a false positive convicting an innocent person is the worst outcome, so we want high precision. Use case 3, stock market crash prediction. Both FP and FN have serious consequences. In this case, we use F1 score, which balances both precision and recall. The rule is simple: if FN is critical, maximize recall. If FP is critical, maximize precision. If both matter equally, use F1 score. Now, let us define these metrics mathematically. Precision equals true positives divided by TP plus FP. This answers, of all the cases I predicted as positive, how many were actually positive? A high precision means few false positives. Recall, also called sensitivity or true positive rate, equals TP divided by TP plus FN. This answers, of all the actual positive cases, how many did I catch? A high recall means few false negatives. The generalized F-beta score is 1 plus beta squared times P times R divided by P plus R. When beta equals 1, we get the standard F1 score, equal weight on precision and recall. When beta equals 0.5, false positives are penalized more. When beta equals 2, false negatives are penalized more, useful for medical cases. In our diabetes example, precision is 91%, recall is 83%, and F1 is 87%. Specificity, or true negative rate, equals Tn divided by Fp plus Tn, also equal to 1 minus Fpr. The ROC curve stands for Receiver Operating Characteristic. Here is how it works. For every possible cutoff value, we calculate the true positive rate on the y-axis and the false positive rate on the x-axis. We plot all these points to get the ROC curve. The diagonal line represents a random model, no better than flipping a coin. A perfect model would hug the top left corner. The area under the curve, or AUC, summarizes the model in one number. An AUC of 0.5 means the model is random and useless. 0.7 is acceptable. 0.8 and above is good. And 1.0 is perfect. An AUC of 0.75 means if you randomly pick one positive and one negative sample, the model will rank the positive higher 75% of the time. Remember the trade-offs. As precision goes up, recall tends to go down. As sensitivity goes up, specificity goes down. ROC is cutoff independent, making it ideal for comparing models. Now we move to an important topic, weight of evidence, or WOE. Question: for a classification problem, how do you determine which features are important? You cannot use correlation. That only works between two numerical columns. For a categorical feature versus a discrete target, you can use the chi-square test. But a more powerful approach is WOE, weight of evidence. WOE has two main uses, feature selection and categorical imputation. The formula is WOE equals the natural log of percent events divided by percent non-events. If WOE is greater than 0, the proportion of events is higher than non-events in that bin. The model will predict class 1 for this category. If WOE is less than 0, non-events dominate, and class 0 is more likely. Why do we use natural log? Because ln is beautifully symmetric around 0. ln of 1 equals 0. Perfect neutral point. ln of x greater than 1, positive WOE, event-rich. ln of x less than 1, negative WOE, non-event-rich. WOE tells you the predictive power of a single feature, bin by bin. Let us work through the WOE calculation step by step. We have a categorical feature x with 4 categories, A, B, C, and D. Total events, 100. Total non-events, 8,000. For category A, 10 events out of 100 gives 10%. 1,000 non-events out of 8,000 gives 12.5%. WOE for A equals ln of 0.10 divided by 0.125 equals ln of 0.80 equals negative 0.22. So category A predicts class 0. For category B, 20 events is 20%. 500 non-events is only 6.25%. WOE for B equals ln of 3.2 equals positive 1.16. Strong predictor for class 1. For category C, 30 events is 30%. 5,000 non-events is 62.5%. WOE equals ln of 0.48 equals negative 0.73. Predicts class 0. For category D, 40 events is 40%. 1,500 non-events is 18.75%. WOE equals ln of 2.13 equals positive 0.76. Predicts class 1. Notice, categories B and D have positive WOE. They help predict the event. Categories A and C have negative WOE. They predict the non-event. Now, weight of evidence gives us predictive power PR bin. But for feature selection, we need one single value per feature. That is where information value, or 4, comes in. The formula is for equals the sum over all bins of WOE times the difference of percent events minus percent non-events. Let us calculate for our example. Bin A, WOE is negative 0.22, difference is negative 0.025. Product, 0.0055. Bin B, WOE is positive 1.16, difference is plus 0.1375. Product, 0.1595. Bin C, WOE is negative 0.73, difference is negative 0.325. Product, 0.2373. Bin D, WOE is positive 0.76, difference is plus 0.2125. Product, 0.1615. Total 4, approximately 0.564. Now, how do we interpret for? Less than 0.02, useless feature. Drop it. 0.02 to 0.1, weak predictor. 0.1 to 0.3, medium predictor. Keep it. 0.3 to 0.5, strong predictor. Definitely keep it. Greater than 0.5, suspicious. Could indicate data leakage. Always investigate. R4 of 0.564 falls in the suspicious range. Worth checking. WOE is also used for categorical imputation. Treat missing values as their own bin. Look at this chart. It shows how accuracy, precision, and recall behave. As we change the cutoff threshold, at a very low cutoff, say 0.1, recall is very high because we predict almost everything as positive. But precision is low because many predicted positives are actually negative. As we increase the cutoff, precision rises sharply, but recall drops because we are being very conservative about predicting Class 1. Accuracy peaks somewhere in the middle, around 0.5 to 0.6 cutoff. This is why choosing the right cutoff matters so much. For production deployment, you either use domain knowledge, consult the business team, or optimize for the ROC AUC curve to find the best cutoff automatically. The PRA crossover point, where precision, recall, and accuracy are closest, is often a good starting point for the cutoff decision. Finally, let us go through the most important interview questions on this topic. Question 1. You have a huge number of rows. How will you know which feature is important for why? Answer. Use information value, calculated from WOE scores. Higher for means stronger predictor. Question 2. If y is discrete, how will you do feature selection? Answer. Again, for using WOE. Cannot use correlation for discrete targets. Question 3. How do you handle missing values in a categorical column? Answer. WOE imputation. Treat missing as its own bin, calculate its WOE. Replace NaN with that score. Question 4. When to use F1 score over accuracy? Answer. When classes are imbalanced. Accuracy can be misleadingly high. Question 5. When is ROC preferred over precision recall? Answer. When both classes matter roughly equally. For highly imbalanced data, use the precision recall curve instead. Quick summary to remember. WOE, per bin predictive power. 4, per feature selection score. Recall when FN is critical, like medical diagnosis. Precision when FP is critical, like legal cases. F1, when both matter equally. ROC for comparing models across all thresholds. That concludes this lecture. Thank you for watching.